Hey again, guys. Thanks for checking in again and again. You're such good students. With this short video, this is almost as short as the other one. The other short one was the first order integrated rate equations. This is a few examples and applications of second order integrated rate equations. Of course, slightly different in form. So we derived this equation and the equation for the half-life of a second order rate in a previous video, and let's apply them in a couple of ways. Oh, let's review what they mean. Let's see. A is the concentration of A originally, concentration of A at a certain particular time t. Here's the time t, and here's a constant that allows us to connect the two. Or in the language of slope-intercept, it's y equals mx plus b. And the half-life for these second orders are interesting because the concentration here originally, that helps determine how long it'll take for it to decay into to half-away, which is unusual as compared to the first order half-life equation, because that does not require is not variable, I should say. Alright, setup of the question. In a reaction described by the following analysis. So here I have a graph, not too surprising. The original straight-up concentration versus time, it almost always slopes down like that unless it's zero order. In an attempt to linearize that, I took the natural logarithm of those y-value data set and replotted again the natural log versus the time, and it looks sort of straight, but not exactly. If you do a linear regression analysis, you'll find the reciprocal equation is actually more straight, or a little more straight, and that's the one we go with. So in this case, the slope of the line 0.053 and the reciprocal of x versus time tells me that again it's second order. A 1.73 molar solution of x in aqueous phase observed over 47 seconds. What's the concentration of x at the end of this time? Well, if you followed along with the previous video clip on the first order integrated equation examples, this is going to look very similar. The math is different. It's not the natural logarithm. As it was with first order. It's the reciprocal, but everything else pretty much stays very similar or analogous. Oops. And so, from the reciprocal of x versus time graph, as this yields the linear analysis, I wrote the rate law, second order, because the reciprocal linearized it, and the constant is that. Although I don't really need this, I was just reviewing what it would look like if I were to get a linear analysis with the reciprocal of x. And so, let me pull the above equation. The reciprocal of the concentration at a particular time equals the original reciprocal of the original concentration plus kT. And there's the constant, and it was 47 seconds, and I started originally at 1.73 molar. So here's where I start, and here's where I adjust. And when I take this positive number and add this positive number, it'll more or less equal this, the reciprocal of this, which in essence makes this larger. And then when I take the reciprocal to find the x, it becomes smaller, so I end up with a smaller amount than I used to have. Let's see. So I found the reciprocal of 1.73 and 0.053 times 47, and you add the two, take the reciprocal, 0.326 molar. So I began at 1.73 molar, and I creep all the way down to 0.326 molar, as described in rate by this constant. Side note, what would be the half-life of this equation? Well, if I know the constant, and I know my beginning amount, 1.73, then the half-life would be 10.9 seconds. In 10.9 seconds, half of that 1.73 would be gone, or decayed or changed into something else. But the interesting thing, one of my interesting points here is that depending on where you start, you'll end up with a different half-life. So if I started with only, say, 1 molar instead of 1.73 molar, my half-life is longer. It takes longer for that lesser amount to decay away by half. And I just rephrase that here. As time goes by in a second-order reaction, and the second-order reaction proceeds, the half-life time increases. It takes longer to decay to half the original value, or half a particular value wherever you're at, the longer the time goes by. Alright, second example. Let's see, what do we have? Oh, a rate constant. It says, what is the rate constant? Which allows a reactant to decay to 43% of its original value in 65 seconds. And again, they told me it was second order, so as soon as I see second order, I pull out this equation. 43%, that's going to confuse me a little bit. They want to know what the 65 seconds, that's the time there, but they want to know what the constant is. What is the constant which allows, over 65 seconds, this to go to 43% of its original value? So here's what I wrote. We're not exactly told the initial amount of my chemical, or the final amount, although I am told the final amount's 43% of the original amount, and that took 65 seconds. So and I just plug the numbers in and do a little bit of algebra, see what I can get. So 1 over 43. So I assumed a 100 gram sample, although everything else will be proportional. Yeah, right. Or the molarity. You could use other descriptions of that concentration, and that constant would change a little bit according to what you chose to use for your concentrations or amounts. But in any case, going with the grams, keeping careful track of my units, reciprocal of 1 over 43, reciprocal of 1 over 100, the time is 65 seconds. Subtract this term over to the other side and then divide by 65, and you find a small number, 0.000205, 1 over gram seconds, which is sort of an odd unit for a constant, but it's because I chose this to be in grams. Alright, one more example for pressure of gases. In a second order decay process with a rate constant of 0.0176, 1 over torr seconds, the pressure of the gas drops from 933 torr to 242 torr. How long does this take? How much time does it take? So here's the reciprocal of my pressure at a particular time t. Here's the reciprocal of my pressure at the original concentration, 933, 242, and the constant was told to me. Now comes the math. So I took the reciprocal of 242, take the reciprocal of 933, the constant is told to me, yes, it is, there it is. And solve for t, subtract this term over to the other side and divide by this small number. Finally, 0.17 seconds. So in other words, this is a fast reaction. Proceeds quickly to completion. Alright, that's it guys, thanks, see you in class.